Who did not enjoy the first lecture? Because you weren't there. You did not enjoy it? Well, I mean, it's probably the same, right? If you can't attend, you can enjoy. Yeah, about that. So we tried to record the first lecture. In the middle of the recording, the battery was empty, so we only have half of the lecture recorded, which isn't a big problem because we already had this first lecture recorded a year ago or 2 years ago. So you should be able to find that in the depth of the web. If you can't, I've uploaded 2 links into the whiteboard, so you should be able to find those. Good. So last week in self-supervised learning, we discussed backpropagation and introduced our favorite models, neural networks, who are composed of layers we called them units, and the whole model maps inputs x to predictions y hat. Now, these layer-wise or in layer organized models are composed of these units, and each unit integrates inputs in a weighted fashion. Integration means summing up, right? So we are in a discrete kind of world. And each of these units computes an output depending on what kind of activation function we have chosen. I showed you sigmoid activations. It's all getting much more easy in the future. We'll use other kinds of activations. We'll come to that in a minute or two. And if we are not coming to this in a minute, Manuel will talk about this in the tutorial. These nonlinearities are really important, and we call them activations, yeah? Or the results of these functions are called activations. Training one of those models requires us to run an algorithm that's called backpropagation. We looked at that, and that was your primary assignment for last week. What we do is we compute the gradient of an error function. So what we want to do is, for a certain location in weight space, so for a given combination of parameters, we want to know the change in these parameters, so direction and amount of change of each of these parameters to improve the error, so decrease the error. Okay? That's what backpropagation implements. And yeah, and that's pretty much it for last week. Anything unclear so far? Please let me know. Any questions still open here? Good. Good. So this week we will look at self-supervised learning, because the previous lecture kind of required us to have labels to be able to compute the loss function, the error, which is nothing that we do have in self-supervised learning, or rather we replace the labels that have been collected by a human, or with the help of humans, with something that doesn't need human labor that much. But in order to understand what self-supervised learning is, today I'm going to show you what unsupervised learning and not self-supervised learning is. Okay, so we're gradually progressing into our target field without looking at it today. Okay, so today, no labels anymore. Okay, we are not interested in unnecessary human labor because we are computer scientists. Okay, we do not want to click images. Good. So I'm going to try to give an intuition or a definition of both fields. Let's start with unsupervised. So unsupervised learning tries to understand the data in its entirety. Okay, so do we see groups of clusters in the data? Can we see certain dimensions in which the data has a lot of spread? Yeah, those kind of things. We obviously don't need any labels for this. We can treat every data point as an anonymous point. We don't know what it is, a cat or a dog. But the shape of the data set, or the shape of structures in these data sets, that's what we're interested in. So the purpose here is exploring these data structures, reducing dimensionality. Have you heard of PCA? Yes. Who has heard of PCA? Okay, cool. Very good, very good. We're going to use that in the assignment. Are we going to use this? I mean, in the paper they did, but I don't know if we. Optionally, we will use this. And grouping data. So this is really like a rough definition of unsupervised learning. So what is self-supervised then? In self-supervised learning, we introduce so-called proxy tasks. Remember when we had the model and an image was mapped into an output vector that represents the probability of the input, I don't know, showing a dog or a cat or a flower. Remember that? In order to train such a model, we needed labels. And now we still want to use the same kind of mechanism to train a model without human annotated labels or data. But in order to actually still be able to use the same algorithm, we need something that replaces these human labels. Okay, and these are proxy, so-called proxy tasks or pseudo labels, and we're going to introduce these a little more properly in the next upcoming lectures. But in the end, what we do to train such a model is basically exactly the same that we did last week, but we just replace the labels with something that we kind of come up with somehow. And this kind of coming up with somehow is exactly the topic of all the rest of this semester. The primary purpose or goal in self-supervised learning is representation learning. Who has not heard about representation learning? Everybody has heard about representation learning? You haven't. Okay, so what is representation learning? I'm going to show you a couple slides, but in the end, really it's simple. What is a representation? Well, it's a set of numbers that describes or well captures the relevant features in the original data point. And the original data point was a set of numbers too, but probably much longer or much larger, and a much larger space. Yeah, so images, I don't know, 1,000 by 1,000 pixels is 1,000,000 dimensions, and good representations are usually smaller, so fewer numbers that still represent the essence of the input. Yeah. Why do we need shorter descriptions of input data? What do you think? What's the advantage of having representations?
It's easier to work with.
Why? Why is it easier?
Because it's
Less data, smaller, easier to handle. Okay, good. Sometimes, and we'll learn about this in the next couple of lectures, it helps you with pretty much everything in the learning process. It makes learning faster, makes learning more robust. You don't have to retrain every model when you have good representations and you want to switch the task. So, but we'll look at that. Now, these line between unsupervised and self-supervised is obviously a little blurred, because sometimes you can think of proxy tasks that you introduce on the self-supervised side as something derived from the entire data set. And that's something that we'll look at today too, through deep cluster, an algorithm that uses clustering, which is more unsupervised, to train a representation of image data. So there's no distinct border between those two. Oftentimes you see that there's some overlap. Okay? Good. So today we're not going to focus on self-supervised that much. We'll focus on unsupervised, because if you know what you do not want to learn about, it's good, or it helps you defining what you want to learn about. Okay? Good. Let's start with the basic setting in unsupervised learning. Let's say we're given an unlabeled data set. And let's keep for now our idea of images. So each of these data points, let me just grab my pointer. Aha. So each of these data points lives in a space of, let's say, 1 million dimensions. And obviously that's too many to put on a slide, so I just drew 2. But really, I mean, this is, let's say, 1 million dimensions, okay? x1 and x2 and x3 and x999,999 and x 1 million, okay? Okay, that should work now. Okay, so let's say this is our data set. It's a small data set, obviously, but maybe I'm not showing you everything. What can you tell me about this data set? What do I want to know, right? I mean, I don't know. What is there to know? Okay, so there's some samples that are close, and then some samples that are far away from each other. Maybe they're like groups, right? These kind of questions one may ask. And turns out that's exactly what we want to ask in this lecture. So for example, we can find data groups. Now, remember, we do not know what these groups correspond to. We do not know whether this cluster here corresponds to Labradors and this cluster to the other species, race of dogs, right? So we do not know that. We may be able to look at it as a human and then label it for ourselves, but the program that runs through these data can't know, because there's no labels, okay? Just a reminder. And also in unsupervised learning, we just don't know how many of these clusters there may be. Yeah? Could well be that this is a blue cluster, or maybe it's 2, a red and a blue cluster. So many unknowns here. So, but let me introduce the clustering problem a little bit more formally. Given is a set of points, and we call them x1 through xn, like usual, and they are m-dimensional. Okay, so in our example, 1 million. M is 1 million. We do also require a distance metric that we abbreviate with d for distance. It could be anything. Let's just for now assume it's a Euclidean metric. So our objective now is to group these points into a number of clusters. And clusters is really defined as neighboring points, such that each of these points is assigned to exactly one of these clusters. So the sum, or the union of all these subsets, is the data set. Okay? We are not forgetting a point, and we're not assigning a single point to two clusters. Okay? And that's it. Assignment, whether a point belongs to a cluster or not, is entirely done through the distance metric d. Okay? Good? And again, we don't have any labels, so it's an unsupervised problem. Okay, let's run an example. Obviously, I like dogs. You probably have already noticed. Let's say we have 6 samples given. And I'm not telling you what the distance function is. How would you group these dogs? Who belongs to whom? So don't look at the position on the board. Obviously, each point is 1 million dimensional. So who is similar to whom? Do you have an idea? No idea? You just look at it. You're a human. You're super intelligent. Okay, so what I'm basically asking is, what are relevant dimensions or features, right? So properties of each of these images that we can use for comparison. Color and size could be one. Do you have another idea?
Direction, where they're looking at. Like
Direction. Very abstract in the sense of high level. Yeah.
the shape of the ears.
Shape of the ears. I love that. Yeah, these little knobby ears here. Yeah?
Maybe also age, like puppy or no puppy.
Age, yeah. So you see,
They're really fluffy.
fluffy dogs, yeah. Aren't they all fluffy? Yeah. But you see, the way you group now these samples together really depends on what the features are. And the way you compute distance, right? So let's take fluffiness, for example. Who's the fluffiest? This guy or this guy? Probably this guy, top left. And so what's the distance in fluffiness between these two? Is it bigger than between these two? Really hard to compute, right? But you see where I'm getting it. So there's like 2 things we need to define: the features and the distance. And the distance obviously needs the features defined, right? Okay. Today we're going to look at k-means clustering. It's a very common, very well-known algorithm. You should know k-means. If you don't know k-means, I'm really happy that you're here. Who knows k-means already? Most of you. Okay, so we can maybe accelerate a little bit. Okay, so k-means clustering basically already tells you what it does, because it finds k many means, so average positions of our data. Okay, and these average positions are here. These stars, again, they represent our data. So these representatives are, let's say, a model of the data set. Using k many means is a very, very simple way, and you can add different extensions or augmentations to this idea, model the spread of these clusters, for example. Yeah, but we're not going to go into this more detailed. In k-means, we have obviously again an optimization objective, something that we want to minimize or maximize. And once we've done that, we know we're done. Yeah, like always in machine learning. And that is, first, given the data, x, capital X is always the data. This should be m, yeah? Can you take note of this so we correct that? And cluster sets, yeah? with respective centroids, mu1 through mu k, which are these guys here, these stars. We want to minimize a sum of sums of distances. So what does this say? We have d between x and mu I. So these are the distances within the cluster of all the points to the respective cluster's centroid. Yeah, so the within cluster distances, and we sum up all these guys. Simple. What we want is this to be minimal. Okay, so given a k, for example here, 3, you can just try that out in your mind or on your computer. When you move around these cluster representatives, what happens to those distances within the cluster? Yeah. So the best fit of these cluster centroids is really in their centers. Yeah. Good. I've created a suboptimal setting. I moved this guy here, and that guy there, and this guy there. And each of these samples is now assigned, obviously, to the closest representative. Okay? Obviously, if you're a point that sits here, you should be represented by the closest of these representatives. Bless you. Okay? And now, comparing that to the previous slide, you can see that or maybe you don't, I hope you see that the intra-cluster distances summed up are larger than in the optimal case here. Yeah? Good. So let's go through this step by step, because we want to wrap that up and come to the more interesting part of the lecture. We start by randomly initializing our representatives. You find solutions or implementations in which you randomly choose samples and put those cluster centers on top of these samples. Sometimes you find implementations of where the data set is processed and normalized either, or you find the boundaries of the data and then put it, uniformly sample positions within these boxes. But anyway, you somehow sample k many clusters. So the respective sets, capital C, I, are empty, obviously, we haven't yet started. And those centroids, mu, are distributed somewhere here. Good. Now, the next step is obviously to assign samples, so data points, to their clusters. So for every point xi, we have to check, is cluster 1 the closest, is cluster 2 the closest, or is cluster 3 the closest? So we are not going, we cannot avoid computing each of these distances. Yeah? So if we have a lot of, or many mu's, mu i's, takes longer, obviously. Fewer mu's is faster. And then obviously we assign the xi to the set that is closest, and that should, and that's the distance calculation, and that should make a coloring. Yeah. So this initial cluster is only closest to these points. This blue representative gets a lot of data here, and the green cluster gets this data. Okay. And now what we do in the next and last step is, okay, if these data points are cluster 1, well, then cluster 1, or the representative of cluster 1, should be in the center of these data points, right? Again, so if these points belong to the same cluster, well, then obviously to minimize the intra-cluster distances, this guy should sit on the center. And that's what we do. We just move this guy to the center of all these points, and this guy to the center of all these points, and this guy in the middle between these two. Yeah? And so how do we calculate this mean? Well, we compute the mean through this, right? So we sum up all these x's in the respective cluster and divide by the number. Easy. One last thing, we need to be able to understand or know when to stop. I've ran this in my head and painted this on those slides for you to be able to understand what's happening. So from here to here, that's the third step, right? So recompute those cluster centers. And then we have to assign the new points again. So we iterate over the second and the third point. And then, of course, we move these again. And then at some point, we have this nice clustering again. That's what you said. Michael said, stop when the distance between the ith cluster center, oh, these should be mu, sorry, at iteration t plus 1, so the next step, and the previous step, if the distance is smaller than an epsilon, then we think that, you know, there's probably not much more to gain in information. Okay? To summing up those steps, we initialize and then we iterate over the assignment and the update step. That's it. Sometimes, and you'll hopefully see that in your assignment, because it's an iterative solution, it depends on the initial choice of your mu i's of the cluster centers, which means you may end up with different clusters and different cluster positions if you repeat the same thing. So you start again with the same k, but because you're randomly choosing your cluster centers, you may end up with a different clustering. And it's not just that you lock in on the same cluster positions and the IDs are switched. Could still and well be that you have different samples assigned to each cluster. Yeah? So a solution to this is you run it multiple times, evaluate those solutions, and decide for which one to keep. I know. Sometimes it's sad. There's no golden path, and it's just muddy waters and dirty data work, but that's what it is. You can always think of our definition of what is the best solution. Yeah? So if you run it 10 times and one of those solutions has the lowest distances summed up over each cluster, summed up over all clusters, then you take that one. Yeah? But yeah, there are many solutions out there. I'm not going to go into detail here. So there are a couple of questions open. Okay, means, oh wait, there's a question. Exactly. How do we know? Well, we don't. We just don't. So what people do is they take, they start with, let's say, a minimal number of clusters and run the algorithm over and over again, increasing the k by some amount, either linearly or on a log scale. Um, so obviously what we could do is we choose the k as equal to the amount, as a number of samples, which was n, which doesn't make any sense, obviously, because the representatives then would represent just one data point. Well, we don't have to do that. But it's OK. We know what the maximum of this is. Yeah. So we probably should choose that. But yeah, that's what we should do. Oftentimes, you'll find that even if you know there is 100 classes or 100 objects in the data set, you get better results when you choose some k larger than that number. Why is that? Why is that? What do you think?
Some subclasses could be closer to each other than the rest of the subclass, so it considers each subclass as a subclass.
So one subclass could be organized as 2, and then you find 2. Yeah, but then you would differentiate between this part of the class and this part of the class. And this helps in other tasks. We'll see in deep cluster that's exactly the case, but no, I'm not referring to this case. But think of outliers. These will probably attract single centroids, and they may not be really important to represent or to understand what the class is about, right? So we'll throw in some of those cluster centers to cover the outliers, which we don't know whether they will find them, right? We just don't know, but they might. And then the rest is extra structure. OK, so we discussed that. Too many centroids leads to overfitting. We don't want to do that. And there's one method that you'll find not just in k-means, but in many of these hyperparameter searches. You vary the k, in this case, hyperparameter, and you see how the quality or the performance of the method changes. Here, the distance, intra-cluster distance, decreases. And at some point, adding more cluster centroids doesn't improve the solution much more. And that's exactly the sweet spot, right? So we want to be somewhere here at k equals 5 or 3, depending on this change in performance that you still want to get by increasing k. That's also your choice again. But that's where the elbow is, and that's why it's called elbow method. You run that screening, you choose your preferred parameter at the elbow. Yeah? OK, more problems. Noise or outliers. Yeah? So points that kind of belong and may not belong to a certain cluster. That is a problem because you can have cluster centers find these and never get out of there. Because other points and other cluster centers will be closer to the rest of the points, which is something that we do not want and which could be something that we want, depending on your use case. Yeah? So if we had chosen only 3 cluster representatives, and the green guy would lock up in here, and the blue guy would probably take these 2, then this would be a solution that we do not want. Yeah? But if we would screen through all solutions with an increasing k, we'll probably find this, with k equals 4 to be a better solution. What about the stopping problem? We do not know a priori how the shape of these point clouds really is. Yeah? It could look as if we have like circles. And actually, one cluster would be the outer ring, and one cluster would be the inner ring. That doesn't work using k-means. There are other solutions to finding these clusters, other clustering methods we are not going to talk about. K-means sucks in this case. Yeah? So k-means cannot or isn't the the first choice, no, is the first choice in trying something quick and dirty, isn't the best choice. So, I don't know, Andy, what would you say? How much time do you invest and how many times do you run over the data until you actually find something that you can sell?
Some month.
Like how many, so let's say the actual solution that you want to propose in a paper or whatever, or to a client, runs through the data set once. How many more times do you have to run it in development or in training?
So for our data, maybe 10,000 times.
10,000 times. Yeah, I would say at least 1,000 times more. Yeah. Just so you know, right? So if you have a very complex algorithm that runs, I don't know, 2 days, make sure you have 10,000 times more time to develop that algorithm. Yeah. So, I mean, especially in the academic context where we do not have any compute, or maybe we do have compute, but it's like tiny if you compare it to what Google and the other big players have. What we do is simplify the problem, simplify the model, simplify the data set, simplify everything to make it run fast, because we do have to run it many, many, many times to understand what's going on, to understand if our solution is good, to understand if another algorithm does it better, and so on. Yeah? Okay, that was k-means. Any questions? So remember, the last lecture we covered learning, and learning in k-means was basically, updating the centroid to the mean of the data points. Learning in pretty much the rest of the semester is this, walking downhill. And now, again, we used this E or L for loss or error to describe the quality of the fit of the model. Yeah? The quality of the fit of the model in k-means was the cluster distances, or the distances of the point to the clusters. The quality of neural network models to the data is output, I don't know, minus the label squared, and sum these up over all samples. And learning takes place through the gradient walking down this parameter landscape. And in self-supervised learning and unsupervised learning with the representation learning overlap, we often want to find good representations, good positions in parameter space that allow us getting a good Z. And Z is often used in the community to denote activations in not the last layer, but somewhere in the middle. Yeah? Not the input X, not the prediction Y hat, somewhere in the middle, some layer, could be the first, could be the penultimate layer. You take out all the activations, and that is representation of the input. Yeah? So usually you have networks that reduce the dimensionality down to something more manageable, like we discussed. And Z is, for example, the penultimate layer activations. And in representation learning, this guy, this Z, represents the input. Okay, so this could be 1,000 pixels by 1,000 pixels, so 1 million dimensional, and this could be as small as 1,000 dimensional, right? So reduction in dimensionality by factor 1,000, which is great. Now, why do we need this guy? Well, we could train a classifier, which could be as simple as just a linear layer, just one weight matrix multiplied to this 1,000 dimensional representation Z, to obtain a class probability vector, right? With some activations, obviously, but this could be a very simple classifier. And the classifier, for example, here decides whether this input in Z space is a cat or a dog. Okay? Well, but how is this any different from what we have done before? Well, the representation Z is learned without those labels. The classifier then can be trained on these. Well, but if we have those labels, why don't we train it supervised? Well, it is oftentimes interesting to have a versatile and robust representation of the input data to be able to train different classifiers. So one classifier that classifies between cats and dogs, one classifier, I don't know, between tongues and no tongues, and maybe a regressor or an object detector on the same representations. Yeah? So we don't have to retrain everything over and over again. We reuse this guy. So we train it on some general objective that produces good. You often find good representations in the paper, and I always smile when I read that because nobody really tells you what good is. But I say it's useful. Yeah, it's useful because there are different uses for these representations. Yeah, you can train a simple classifier. Simple meaning low, like only few parameters, just one linear layer. Not many layers, not big networks, because most of the legwork is done here. Yeah, and then we can have the regressors and all these different things. So this is representation learning, but we do this often for other purposes, or sometimes these purposes overlap. So if we have a reduced dimensionality, things are smaller, are faster. Remember, we need to be fast in academia because otherwise we just won't find an end, or we just have to wait so long and the conference deadline has passed. Sometimes training a good and useful representation Z circumvents certain errors in the network. For example, self-supervised learning objectives may be less prone to overfitting. Yeah? And we make efficient use of data. Obviously, we don't want to train a network for this task, a full network for the other task, and a full network for this task, just because we care for the environment. Okay, should be a reason to put on the slide as well. So for the remainder of today, I'm going to present this paper, which was put on archive in March 2019. So it's already 4 years old, which is like 2 decades, in machine learning standards. So it's pretty old, and you probably won't use it in your real work or work life then. But it shows you a couple of interesting approaches to solving a problem. It shows you how to measure different things, how to use those representations. If you read the paper, it's a pretty straightforward paper, easy to read. It gives you a gentle introduction into the field. And that's why we chose that. And the idea is pretty simple. You have input images again. You have a convolutional network that creates representations. On top of these, and it doesn't show here in the figure, there is a classifier, again a linear classifier, just one layer, that maps it to a distribution of output classes, but these are trained such that the network is made to reproduce a clustering that is obtained by k-means. Easy, okay? And we'll look at that in detail now. Before I continue, I should ask you, Who knows what a convnet is? A convnet. Uh-oh. Okay, okay. You know? Yes, a little bit? Okay. Okay, so I think we should cover that. I have added 2 more slides, which may still not be enough for those to understand who don't yet know what a convnet is. Maybe I should be drawing things. So what we did discuss is that this be the input x. So each of these circles here represents a number. Okay, so this could be 0.9, this could be 12, this could be minus 42, and this could be 32,111, right? Whatever. And then we said, okay, we do have intermediate units, and these are connected, right? So each input neuron or unit is connected to each of these intermediate units. And since everyone is connected to everyone, this corresponds to a weight matrix W, and we call this W with a superscript 1. That is last lecture. And we see that many of these connections, this is a lot. So all these connections are in this weight matrix. And by the way, we do have an additional bias term, right? So this is the bias, and then all these other connections feed to these units too. This is a lot of parameters, yeah? And if we had 1 million input neurons or units, so 1 million input pixels, one of these dimensions would be 1 million, yeah? And then depending on how many we have here, it could be 1 million times 10,000 or so. So it's huge. And that's bad. Yeah? And it's not just bad because it's huge, it's also unnecessarily huge. Close your eye and just look at the world. Objects are spatially correlated. So everything that I see and that I can think of as an object has spatial consistency. Right? So so each pixel, I mean, if I had pixels on my camera, in my eye, each pixel corresponding to an object they're spatially correlated. They're populating this kind of same region in 2D space, and that's cool. I mean, it's cool because physics work like that, and it makes the world much simpler. But it also makes our work much simpler. So the idea is if we have images or data that does have this spatial or sometimes also temporal correlation, right? So if we have time as a dimension and, I don't know, voltage, I don't know, brain signals, or if we had an audio recording, right? So if I say a word, like word, the object word, this guy, is correlated in time, right? So all samples within this object, they are close together. So, and dependencies, certain patterns, how this waveform looks like, or in images, right? So corners, shapes, shades, colors, and all these things. These correlations are local. And this very important property can be leveraged and can be used in convnets. So what we want to do is we remove most of these connections. We reduce most of these parameters to the most likely ones that we have to use to learn patterns. And these are the ones that in images are around a certain area, right? So if I had a picture of a dog, for example, there's a lot of stuff going on in the vicinity of a certain pixel. But if I look at patterns of dog noses, it's very unlikely that pixels that are far away have any influence on the shape or the color or any other feature of the nose. Yeah? So, I mean, yes, there could be a mirror, and you could see the nose in the mirror. Okay, I give you that. But, like, most of the time, in the vast majority of samples, nose pixels are on the nose, period. And so that motivates convolution. Convolution is basically taking your parameters and multiply them in this sequence, in this fashion. I'm going to repeat that. Step by step on your sample, over your sample. Multiply meaning so for a given position, let's start with the first position. So we only have black pixels, and black means -1, and bright pixels, and bright means +1. And the same for our parameter, which already is learned, let's say. So we have found parameter values. And we put this on top of the image here and multiply each respective pixel of the so-called kernel with the underlying image. Louis made this beautiful presentation here, so I'm going to run it a couple of times. Yeah? And each time we've multiplied the kernel or the mask to the underlying image, we write the result in one result cell, in one result image, let's say. Yeah? So the result of the first convolution here is 1 times -1 plus this times this plus this times this. Yeah? So what we do is basically a dot product again. Ooh, dot product. Did I tell you I like dot products last lecture? I should have. I probably did. Yeah? So what we do is we compute the dot product of the kernel and the underlying image, write the result into this first location here, take the second position, the third position, and so on, and write all these values in here. And what this means can be visualized if I click one more further. You see there are two maxima here. Where are these maxima located? Yeah, it's not the center. It's in the center of these patterns that this kind of searched for. So what we basically do is we have a pattern, and through the dot product, which is a similarity measure, remember that, we scan the image, and the result tells us where this pattern could be found, yeah, in these locations. Okay, so in convolutional networks, we learn one, in this case 3 by 3, so 9 parameters, instead of 1, 2, 3, 4, 5, 6, 7, 8, 9. Let's say this is also 9, bless you. 9 by 9 is 81. So a fully connected layer would have connections from 81 to, I don't know, 10 or so. Let's say 800 parameters, and this solution only has 9. And we do apply the same parameters everywhere in the image, but we use the same parameters. Yeah? So every input is connected to the next layer, but they don't have their own parameters. They share, all these image locations share the same set of parameters. Yeah? And you can still think of the input times a weight is the activation, or is the integration. Then you have an activation function around it. But this matrix now looks a little weirder. Yeah? And it has copies of the same parameter in there. Yeah? Okay, I think this is as deep as I wanted to go in there. What do you think? Yeah? Questions?
How do you determine the 3 by 3 set of parameters?
This choice is a hyperparameter. You don't know which one is good. You have to run and screen them and see what turns out best. So in the history of convolutional networks, people started with really huge kernels, 12 by 12, 11 by 11, or 7 by 7 or so, and it settled at smaller ones, but rather use many, many layers. Yeah, I can upload a couple of video links for you. You can watch these. Yeah, maybe one more thing. So you can think of each of these kernels as a certain image feature. Let me go back to the dog again. If we think of 3 by 3 image features, what kind of stuff would we expect? So the world at this 3 by 3 pixel scale consists of not much. Consists of edges, maybe I don't know, certain color blobs or so. No, at this scale, it should be just edges or corners. Yeah. And it's obviously not just one feature. Yeah. So you use in convolutional networks, you use many of these. So the input is mapped to an intermediate representation using this one kernel, and then you take a second kernel and have another layer of intermediate representations, and you take a third kernel, and so on. So you can play around with yet another hyperparameter, which is the number of features that you want to learn. And your input, which is width by height times 3, y3, RGB for color images, yeah. Could be 4, could be 1, but 3 is pretty common. This image tensor is mapped to an intermediate tensor after the first layer, and its depth is corresponding to what? To the number of features. Yeah. Let me draw that, and then we should continue. So you see, or maybe I should do this for you on this side. So you often see this as this three-dimensional sketches. So this is 3. This is the height of the image, and this is the width. And then you have a kernel, the one that I showed you, which was just this 3 by 3 matrix. These kernels now see, let's say, 3 by 3 by 3. So these are now 27 parameters. Actually, not 27, but how many do we have here? I mean, 3 by 3 by 3 is 27, that's true, but it's not just weights, it's also
28 because of one bias.
28, one bias, right? So we always have 1, 1, and then this is added. This is a bias, right? So this is B here, added to the sum of weighted pixels. And then these 28 parameters are scanned through the image step by step. Manuel will show you exactly what other hyperparameters are, stride, for example, and padding and all these things. But one of these dot products creates one number. And if we take another feature, another set of 28 parameters, it creates another number. And another feature, another number, so that in the end, we do have another tensor. And this is the number of features. Yeah? And then we can do this again and again and again, learning masks that now see all the features at a certain image location. What is he doing? Okay, remember that slide? And that's exactly what the network learns. So these activations, this tensor here corresponds to the like lowest level of features, right? So 3 by 3 patterns, small patterns in the image. And the next layer consists of features that look at a 3 by 3, for example, region of features. Does it make sense? So, for example, one feature looks at diagonal edges. Another feature, so this first layer here is diagonal features. This next feature has like corners, right? So if I have a convolutional kernel that looks at this image block here, or at this activation block here, it integrates diagonal edges, corners, and all these things at this image location, with a neighborhood of 3 by 3, right? And 3 by 3 here means a larger area here. Yeah? And that's why we go from pixels to low-level patterns to high-level patterns. I mean, obviously, there are many, many more steps in between. It just doesn't make sense to write, I don't know, 50 layers or 100 layers or so for you. But this is the general gist of conv layers, what they do. Okay. Questions? No questions. You can ask any questions anytime. You don't have to wait until you meet Manuel. Yeah, you can if you have a question, like think, okay, what the heck am I doing here? Just, I mean, we are not so many. We should be waiting for some of you. If you don't know what we're doing here, let me know. Good. Okay, so deep cluster uses convnets. Convnets are these guys. So we map input pixels to ever increasing abstract features. And activations, so let's say we have like 50 more layers of these. And then we have one of the, I could write it. Let's say at a certain depth, we do have these, and these blocks get deeper and deeper. Let's say we have a block like this. So let's say this is the 50th layer. This represents the input. And Deep Cluster now intends to find a good and useful representation, basically meaning we would like to train a network, so find the optimal parameters such that these blocks of numbers here are good representations of the input. Okay? That's our task. So how do we do this? Again, 3 steps. It's always 3 steps. Again, our data set. And it doesn't look like the one that we looked at before. Why is that so? Well, because we have initialized our network, which is AlexNet. And for those who don't know AlexNet, that's OK. It's one of the very early ConfNets or ConfNet architectures. We use a randomized AlexNet and project an image to a Z. So it cannot look the same. Obviously, I mean, they're made-up dimensions anyway. And we run every x through f, obtain a z, and put it on the slide. Okay? And obviously, we still don't have just 2 dimensions. We have probably, I don't know, a couple of thousand, yeah? At least a couple of hundreds. But the cool thing is that although this is a random network, these point clouds aren't random. Why do you think this is?
There's the Lindenstrauss lemma that preserves distance.
I don't know the Lindenstrauss lemma. What is it?
It's basically a central result in random matrix theory, I would say, that says distances are preserved under random projections with high probability.
Yeah. I would have guessed so, but it's even, so remember we have convolutional networks. So we are not randomly projecting. There is structure in the projection that we impose on the data. Because remember I may want to go into detail here. Okay. So you said random projections preserve distances. And why is that an intuition for you? See, if you have your input and we put it to the left, it doesn't matter where we put it because it's random anyway. So we have our input x and we multiply it by random vectors. And what are random vectors? Well, it's a vector that points there, a vector that points there, a vector that points there. So we basically embed our samples, or we project these samples onto these random projections. So, oh, that's the wrong way. Let's say we are in 2D. Then our matrix is also 2 by 2, right? So we project 2-dimensional samples to a 2-dimensional space. And let's say this is our random vector, and they don't even have to be orthogonal. This is another random vector, R1 and R2. Then our samples are projected onto these guys. by this process. So multiplying each column with the input. Yeah. So these are random projections. Each one is orthogonally projected down so that this point here with its coordinates x1 and x2 is then this number and that number. Yeah? So let's say x bar 1 and x bar 2. And that doesn't really matter where those random vectors point to. If I have a point here that is similar in the original space to this one, then it will end up close also in projection space. That's probably the lemma that you're talking about. And why is that? Well, because it's linear, right? So this whole projection is linear. This convolutional network isn't linear, and we do have this convolutional structure. But still, just think about what each of these parameters is doing. We're looking really at very small spaces, neighborhoods in the input, and we randomize these parameters. Those parameters are randomized. So what kind of structures do we look for? Yeah? And the same logic applies if a sample is similar to another sample, it's likely that they share those features even if they're random. Yeah? Okay. So that means that even in our early representation that we get out of AlexNet, even here in this space, close samples are likely similar. Okay? So the next step that we do is we run k-means. We know what k-means is. Everybody knows what k-means is. We've made sure. And we kind of over-segment. So they do this on ImageNet. Everybody knows what ImageNet is? Who knows what ImageNet is? You know? Only one, two. What is ImageNet? It's a lot more images. I think it's 14 million images, and we have 1,000 classes. And the cool thing about ImageNet is that, bless you, they are balanced. So, you know, it's like dog breeds, right? So German Shepherds in Germany are much more common than, I don't know, Shih Tzu, I guess. That's my intuition. But on ImageNet, they have the same frequency, yeah? The same number of samples showing German Shepherds and Shih Tzus, because that makes things easier, also for training. And ImageNet was, and still I think is, a tough challenge because it's so big. Yeah, 40 million images. Do you remember the shape of or the size of the images? I don't know from the top of my head. 2 to 4, just that small? I thought it was bigger. Why did I mention that? Yeah. So we have 1,000 classes, and we run this guy or this k-means with a k of 10 times more. And I'm going to give an intuition of this later, but for now, just compute that in your head. We have our z space, which was random. We embedded our samples into this space, and now we run k-means with a lot more, many more clusters than we actually know we have. Okay, good. So we might end up with kind of this setting, yeah? And each of these clusters now, I mean, we don't know whether it's a German Shepherd or an elephant. We only know, well, this is cluster 1 and cluster 2 and cluster 3. Yeah? So we use these cluster IDs as pseudo-labels. What does that mean? Well, we will use this in training F, the network, and we'll tell it to predict these cluster IDs. So we tell it to put images into the same bucket that have the same ID and discriminate between samples of different clusters. Yeah? And we do not care about whether samples that are in similar subregions are classified. They're as far away, let's say, as 1 and 5, okay? Because it's a classification task, okay? There's no notion of similarity in a classification task. It should only put all those samples in bucket 1 if they're from cluster 1, only in bucket 2 if they're from cluster 2. Okay. So what we do is now we use a classifier, which is, again, a linear classifier, just one matrix, one weight or parameter matrix. And that projects to a 5-dimensional space because we have 5 clusters here. And of course, this we just started this process. C is random too. So we have a random projection to a 5-dimensional space from a random embedding space, Z. Yeah? Good. But now we can compute an error between what C was doing and what we want the whole system to be doing, which is this point, for example, should be projected into a vector that is 1, 0, 0, 0, 0. Have you heard of one-hot encoding? Yes. So for those who haven't, those labels here, those pseudo-labels, how do we represent them in the computer? There are many ways we could do this, but one standard way is that 1 will be translated to a vector that is a 1 only at position 1 and 0 otherwise. Yeah? So that's 1 hot encoding because only 1 is hot. Yeah? And then obviously 2 has the 1 in the second position, and the 3 has it in the third position. Okay, so we can compute our error of, or like a distance between the actual output of the whole system and these one-hot encoded pseudo labels. And then we can backprop the gradient of this error or this loss, not just through the classifier, but also through the entire function f, through the entire model, which means we are not only improving the classifier, we also try to tweak the features, the convolutional features, such that the classifier has an easy kind of game here. Yeah? All right. Does it make sense? Maybe? Yes? No? Nodding? No nodding? Yes? Okay. And that's basically it. We repeat point 2 and 3, so we run through the entire data set in batches, obviously, and we optimize the network, and thereby changing this space, obviously. Yeah. So the features are different. Z will be different. And since it's a nonlinear function, it's not just it's not just linearly deformed. It's really stretching and pushing things and moving samples to certain spaces or subspaces to improve C, or to improve the task that C has. All right. That doesn't work. Summary, just written it down for you here. We don't have to read that. Now, the cool thing is that although we do not know anything about elephants and dogs and cats, the AlexNet, the model, learns features that kind of are plausible, that look like the features that we get when we train it in a supervised fashion. So as if we would know what a dog or a cat is. Yeah? Well, that's pretty cool. I mean, if you think about it, it's pretty cool. They do introduce something that we haven't talked about, which is Sobel filtering. Sobel filters are basically processing the images to detect or to augment the edges. So it's basically a first order derivative of the image, and that's why if you use these samples, the network learns features that are much more edgier than if you don't use Sobel filtering. Which kind of makes sense because, first of all, they have to run Sobel filtering on gray value images, so there's no color anymore. And also, but they say that the whole training process, so the whole clustering using these cluster IDs as classes process to backprop and improve the function makes more sense or works better if they use the Sobel filtering. And once that's done, they show a couple of things that you can then do. For example, they look at certain filters in the penultimate layer, so the last layer before the classifier, before the last layer. And remember, each of these slices corresponds to a certain feature, to a certain convolutional kernel. And you can sum up all these. You take one slide, a slice, so for example, the first one, or the 33rd, and all these, and you sum all these guys up. And then you process the whole data set and take the top 9 images. So images that appear to have high values in these given slices. And what you see is that some filters seem to have learned object identities. So some filters are exclusively on when a certain type of architecture is shown, or cars are shown, or piano boards are shown, or dogs are shown, or even cats. See? So that's cool. there was a paper even earlier than 2019. I think it's 14 or 15 or so, by a guy named Josinski, and he even showed that although in ImageNet there are no faces, or there are faces, but there's no face class. So there's no class among these 1,000 outputs that says face. Network models trained on ImageNet find faces, represent faces. So one of those slices could represent faces, right? So they would light up, not the entire slice, but rather, because these are convolutional activations, if you take, so you take a knife and you cut it open, yeah? You take one of these slices out, whoop, and then faces would light up in locations where they are. Yeah? And that's cool because nobody told the network to know what a face is. It kind of found out itself. All right. Oh no, wait. Oh yeah. So then let's come to the question of how to evaluate a system that doesn't know what a dog or a cat or an elephant is. How do we know that these representations are good? How do we know they are useful? Well, it's straightforward. We use those representations on different tasks in which we do have those labels. Like, for example, ImageNet. They do have another data set that's called places, and they have they show, I think, 2 more tasks that I'm going to hop over here because you can read about this yourself. And they train the classifier on ImageNet labels. So remember this, this classifier here, this is thrown away. So this was the classifier that was supposed to predict the cluster IDs. This guy, this C, is thrown away, and a new linear classifier is trained to classify ImageNet labels. So output is 1,000 dimensions. Yeah? The other one was 10,000. So we go through the network, through the data set, through all those 14 million images, embed them into the Z space, and train the classifier. So we freeze everything, so the entire network is untouched. Only the parameters in the linear layer are tuned, are optimized. And for AlexNet, we only have 5 convolutional layers, so it's a pretty early network, pretty shallow network. And we take out all those first layer, second, and so on, 5th layer activations, train the respective linear classifier, and then we can quantify how good that works. Yeah? And it turns out that if we take early activations, it's pretty shitty, and it gets as good as 40% of, I think, correctly classified samples, which by that time was pretty good. It's much better right now. And also back in the day, these results are from AlexNet nets that were fully trained and supervised in a supervised fashion, right? So these guys could fully see, so all the parameters were tuned to optimize the error with respect to the labels. And so we see that there's a huge gap, still a huge gap. So those representations that that cluster, deep cluster learns or finds are not perfect. Yeah? Okay. Questions here? mute. All right. I want you to read the paper. As I said, it's a pretty simple paper, straightforward. We put it up on the whiteboard, and you are supposed to implement deep cluster. There are a couple of things that you need to be aware of. They're all described in the paper. For example, they do not use the raw representations here. They use a PCA of that, I think, to reduce the marginality here. And there are a couple of things that could happen in k-means. For example, that clusters turn out to be empty or only have a few samples in them. And training on these pseudo-labels potentially can fail, can turn out to be, could, for example, collapse, right? So there's only one big cluster and all the others are empty, which doesn't make any sense to, as a training objective for a network. But you will read about how to mitigate this, and I'm really looking forward to seeing the results because I haven't trained it myself. I don't even know how frequent these problems are. So I would love to learn about that. Good. So summary. We're pretty early, are we? No, pretty late. Are we late? Sorry. So then I'll just accelerate this a little bit. So unsupervised learning and self-supervised learning are pretty much in the same boat, right? It's no labels territory. We got to be creative when we are doing self-supervised learning, how to get pseudo labels or any other information to be able to optimize anything. This lecture showed you k-means and deep cluster. Deep cluster kind of requires k-means. By the way, you don't have to use k-means. You can use any other clustering algorithm. And the real self-supervised learning lecture will start next week. That was the lecture. Thanks.